Alright, here we have a pumpkin, and the pumpkin is falling. We need some falling lines here. There you go. Alright, here we have a pumpkin that is 36 kilograms. Nice big pumpkin. And it is falling to the ground, and it's going to hit the ground. And let's say it falls for, let's go with 4.2 seconds. So our pumpkin is going to fall for 4.2 seconds, hit the ground, and then when it hits the ground, it is going to get all squished. Okay, so when it hits the ground, it's gone for 4.2 seconds under the force of gravity. It is 36 kilograms, and we're going to find out a couple things about the situation. We are going to find out, first of all, let's find out the impulse when it actually hits the ground. So we're going to look for the impulse when it's the ground, and we'll just start with that. Okay, so when the pumpkin is falling down, obviously the force of gravity is acting on it, and that force of gravity is acting on it for 4.2 seconds. Well, if I've got the force acting on it and I've got the time acting on it, I can actually calculate the impulse on the way down, because impulse, or change in momentum, is force times time. That can be any force, including the force of gravity. So if I do the force of gravity, which is mg, times the time, I can calculate how much momentum the pumpkin gained when it was on the way down. So if I do the 36 times 9.81, and that's about 350 times the 4.2 seconds, we're looking at about 1,480 kilogram meters per second of momentum. So that's how much momentum it gained on the way down. Well, if that's how much momentum it had on the way down, that's how much momentum it is going to lose when it stops, because it goes from rest and falls down, and it gains momentum, and when it hits the ground, it loses all of its momentum because of its squishing and hitting the ground, obviously. So when you get to the ground, it's going to lose all that momentum. So the change in momentum of the impulse would be, we'll say, negative 1480, and I'm going to say it's negative because it's being lost. So that would be the impulse at the ground. Now that we have that, let's see if we can find something else. Maybe, let's say it stopped in a really short amount of time. Let's say it stopped in 0.073 seconds. So that's how long it took for it to squish. So let's see how much force was used to actually stop the pumpkin at the ground. Alright, well, to find this, I'm going to actually use the same type of expression as here. If I want to find out force, force is just impulse divided by time. And I know the impulse when it hit the ground, the impulse is 1480, and I gave myself the time, 0.073. So all I have to do is divide those two out, and I can have the force that was used to stop the pumpkin. And so if we calculate that, I'll round off a little bit, we're looking at around 20,000 newtons. And since this was a negative impulse, you could say that's a negative force, or you could say the force was going in an upward direction. It would actually be the normal force from the ground pushing back up against the pumpkin. So it's the same expression. We worked it this way in order to find the impulse, and then we sort of reversed the expression to find the force that was used. And again, you could use F equals ma using VAT and all that kind of stuff to find it, but using momentum and impulse is another way to do the similar types of questions. Okay, so next let's try a different type of question, make up something else here. So let's get rid of all this. All right, let's try something else. How about this? Let's draw some grass. Get a tree going here. All right, something like that. All right, there we go. Okay, so suppose we have, let's suppose we've got a ninja, and the ninja is doing some target practice with his ninja stars. So he's got a little ninja star going on over here. There we go. Okay. And he's taking a ninja star and he's throwing a ninja star at a tree in order to practice his ninja starring, whatever it's called. Alright, so let's say the ninja star is 0.18 kilograms and he's throwing it at a constant speed towards the tree. And when he hits the tree, obviously it goes into the tree and it stops. and let's say 46 newtons actually stops the star in, let's say, 86 milliseconds. All right, so let's see if we can find out how fast, velocity, find out how fast the star is going, speed or velocity. Let's see how fast the star is going when it's going towards the tree. Okay, well, let's see what we can do here with the information that we are given. Over here, we just have the mass. There's not much here, but over here we've got force and we've got time. And with force and time, we can find impulse. So I'm going to start with that. So the impulse would be force times time. So I've got a force of 46. My time is 86 milliseconds, so that's 86 times 10 to the negative 3, or 0.086 seconds. So if you multiply those two things together, we get an impulse of about negative 3.96. And I'm saying it's negative because the star was stopped when it hit the tree. Well, if that's how much impulse there was, if that's how much momentum was taken away from the star, that must be how much momentum it had when it was flying towards the tree. So over here, it must have had a momentum equal to 3.96 kilogram meters per second. So when it hit the tree, it could be taken away when the star was stopped. Well, now that I know how much momentum the star had, I can find the v rather easily, just the momentum divided by the mass. So I take that 3.96 and divide it by the 0.18 kilograms. I'll round off a little bit. We should get right around 22 meters per second or so. So that's how fast the star was going when it was going towards the tree. All right, so let's try a third scenario here. So let's get rid of this. All right, let's try something else. Let's draw sort of like a hill. And let's say up here we've got somebody on a skateboard on top of the hill. And let's say at the top of the hill, let's say they're going 5.2 meters per second. They're going to go down this hill. Let's say this hill it's a pretty big hill. Let's say it's 28 meters long, and down here, let's say they are going 18.6 meters per second, and they're going to go down the hill. Okay, and let's say also there's a force pulling them down. Let's say there is 350 newtons actually of 350 newtons of force pulling them down the hill. Okay. Now, what we're going to do is we're going to see if we can actually find out what is the mass of the person. Okay, now, you might just want to jump in with 350 divided by gravity because gravity is pulling them down. Well, it's not quite that simple because they're going down a ramp. It's not like free fall or something like that. So we're going to see if we can find out a few other things. Just based on what I've got, I'm just going to see if I can find some simple things. Now, the first thing that pops at me right now is I've got a distance. Well, with distance, I can find time if I have my v's. Well, I've got my v's, which means I can find my average v. Okay, so I've got my first v of 5.2. I've got my final v of 8.6. I can piece together my v's, both my average v as well as my change in v. So I'm just going to do that using my v's. So just adding those up and dividing by 2, I get an average v of 11.9 meters per second. And for change in v, it's just 18.6 take away 5.2, which will leave me with 13.4 meters per second was the change. All right, now I could try and I can do like acceleration v over t and f equals ma and that type of stuff, trying to figure it out. But I'm just trying to use some momentum ideas, sort of piece this together. And speaking of momentum, I do have something I can find with this. I do have the force here, and I could find impulse if I only had the time, but I don't have the time. We'll see if I can find time. I do have a distance here as well as my average v, and with distance and average v, we can go back to the basic formula, times distance over average v, and we can calculate how long it takes to go down the hill. So if we do that 28 and we divide it by the 11.9, we can find that it takes about 2.35 seconds to get down the hill. Well, now that I have force and I've got time, I can find impulse. So my impulse is going to be force times time, 350, times the 2.35, which gives me 824 for a impulse. Now that's not his momentum at any point necessarily, because he's not starting at rest. If he was starting at rest, that would also be the momentum at the bottom, but it's not, because he's not at rest at the top. He's got momentum here, he's got momentum there, but I know the difference between those two momentums is going to be 824. So we're going to see if we can use that idea to sort of piece things together. So if I use that impulse idea, I know that impulse is also the difference between two momentums, which could be mv2 minus mv1. Now I can't solve for either one of these individually, and m is what I'm looking for. So what I can do is I can actually factor out the m, something like this. But v2 minus v1, that's just my change in v, which I had over here. So impulse is equal to force times change in time. Impulse is also equal to m times change in v. So I'm just going to rewrite that. Impulse can be both force times change in time, but it can also be m delta v. Now notice it's delta v, not just v by itself. Well, let's see. I've got the force, I've got the time, I found that over here. Delta v I found over there. Mass is the only thing I don't know. So if I rearrange this, I can get mass is going to be F delta T, or the impulse, divided by the change in V. So this would just be the 824 I had over there, divided by the 2.35 over there, and I can divide the two out to get his mass. And give or take round off, we're looking at around 61 kilograms. Now this is just one way to do the question. You could have done basic Newton's laws as well. You've got the change in v here, you have the time here, so you could have calculated acceleration, found the acceleration. Once you had the acceleration, you could use Newton's second law, mass is force over acceleration, and calculate it that way as well. So it seems like a lot more work doing it the momentum way, but most people who've done this before wouldn't necessarily write all this. They could just jump right to this. So it ends up being about the same amount of work anyway, but it's just a different perspective or a different way to look at the question. Some people like to use momentum in something like this. Some people like to use the basic F equals ma VAT type stuff with this. Some people will go back and forth. It doesn't really matter. There's just multiple ways to do questions like this. And the more ways that you know how to do it, the more types of things you'll have to choose from, more strategies you'll have to choose from.